twisted, glistening, steaming landscape, dotted with conical hills, pitted with craters, broken by fissures. Sharp visual reminders that the island of Hawaii is made of volcanoes. Mauna Loa and Kilauea volcanoes on this island are still active and provide scientists with a dramatic natural laboratory in which they can try to answer important questions. Why do the volcanoes erupt? And why are they growing in the middle of the Pacific Ocean? How can geologists understand what is happening deep underground beneath the volcanoes? What is the source of the molten rock? And how does this lava construct such gigantic volcanoes? Before examining these questions, let's take a few minutes to watch some spectacular activity that is typical of Hawaiian volcanoes. A composite eruption that adds a new layer of lava to the island from its summit to its submarine flank. Here, a flood of lava erupted from a vent in the background plunges 100 feet into an old crater. Roaring jets are driven by rapidly expanding volcanic gas that carries clots of lava high into the air. This fountain rises to a height of nearly 2,000 feet. Basalt is the main type of lava in Hawaii. Its temperature is a little more than 2,100 degrees Fahrenheit when it is erupted, and it is a very fluid variety of molten rock. Some flows slow and become masses of tumbling, glowing blocks. Everything in the path of a lava flow is subject to destruction. Roads often serve as natural channels for lava, moving down the volcano toward the sea. When flows reach the shoreline, they drip and ooze into the ocean from bizarre spigots and tubes. Fed by these spigots, hot lava is quickly chilled underwater to create a thin black crust. The rounded, tube-shaped bodies continue to expand from within and are called pillow lava. On land, when a small amount of water mixes with lava in the vent, the result can be a violent steam-driven eruption, such as this one in 1960. Even more violent eruptions of this type occurred in 1924. Explosions hurled blocks and ash many thousands of feet above Halemaumau crater at the summit of Kilauea. One overly curious onlooker was killed by falling debris. The most violent steam eruption at Kilauea in the past several centuries occurred in 1790. It blanketed the summit with deposits of blocks and ash many feet thick. Layers resembling sand dunes were formed by the clouds of hot ash that surged outward from the source of the steam explosions. Hawaiian warriors, caught in these choking surges, left footprints in the soft ash as they tried desperately to escape. About 80 warriors suffocated, and their bodies were found days later by their comrades. Most Kilauea eruptions, however, are safe and attract many tourists, as well as some Hawaiians who continue the practice of their ancestors and offer gifts to Pele, the goddess of these friendly volcanoes. Modern offerings include money, food, and beverages. Pele, shown in this painting, is said to reside in Kilauea caldera. Professor Thomas Jagger was among the first scientists attracted to Pele's home. He and others recognized that Hawaiian volcanoes offer an ideal opportunity to study eruptions at close range and relative safety. So in 1912, he established what today is called the Hawaiian Volcano Observatory. Part of Jagger's research was carried out in the office and the laboratory, where he developed important new concepts. Most of his work, however, was in the field, observing and measuring details of eruptions. Some of Jagger's early work may appear primitive from a modern perspective, but his efforts established a scientific basis for understanding Hawaiian volcanoes. Jagger opened the gate for following generations of equipment and ideas. The present observatory, operated by the U.S. Geological Survey, is on the west rim of Kilauea caldera and is a world-famous center for volcano research. Halemaumau crater in the background is often the site of an active lava lake. A brief look at the thin crust on this lake can help explain the geologic setting of the Hawaiian Islands. The surface of the Earth consists of about a dozen huge pieces or crustal plates that are in constant motion relative to each other. Geologists call this global plate tectonics. Some plates of crust on the lava lake grow away from each other along zones of lava upwelling about 3 feet wide. On a much larger scale, but in similar fashion, plates on the Earth's surface move away from each other along zones of lava upwelling. Some plates of crust on the lava lake converge, collide, buckle downward, and disappear into the pool of molten rock below. And some plates of the Earth's crust also converge and plunge downward. Together, the convergent and divergent zones form boundaries of the plates. Most volcanoes are along these boundaries. However, some volcanoes, like those of Hawaii, are within the plates. The Hawaiian volcanoes are part of a chain that is progressively older to the northwest, away from the island of Hawaii. The entire chain is thousands of miles long, and its oldest link began to form about 70 million years ago. About 4 million years ago, this volcano in the Hawaiian part of the chain was active. Magma rises from a partly molten zone in the Earth's mantle below the moving plate, about 30 miles or more beneath the seafloor. The volcanoes are carried away from this magma source as the plate moves northwestward about 4 inches per year. Geologists call the source of magma a hotspot or melting spot. The origin of the hot spot is unknown. The age progression that characterizes the island chain is also seen at a much smaller scale within the island of Hawaii. Kohala is the oldest volcano on the island. Lifespans of adjacent volcanoes overlap. The general pattern, however, is one of younger ages to the southeast, where the active volcanoes, Mauna Loa and Kilauea, are located. This age pattern continues even farther to the southeast, where geologists recently discovered an active submarine volcano called Loihi. Loihi may someday grow above sea level and merge with the island of Hawaii. At present, however, Loihi is nearly 3,000 feet below sea level and is accessible for direct examination only by manned submersibles. Mauna Loa, the largest volcano in Hawaii, rises 5.5 miles above the sea floor and is 150 miles wide. Mauna Loa is called a shield volcano because of its broad, gentle profile. Scientists have discovered that shield volcanoes swell before an eruption, as if an imaginary underground balloon were inflating. The inflation causes the summit to rise. This rise or uplift is easily measured by precise leveling, a widely used surveying technique that can detect changes of a fraction of an inch. Inflation also causes the land surface to tilt. Tilt is measured by a variety of methods. The one shown here determines the elevations at the corners of a triangle, again by the technique of precise leveling. Tilt can be measured to less than 1 part per million, equivalent to the slope caused by placing a thin coin under one end of a carpenter's level 3,000 feet long. Reference points on the swelling volcano move apart during inflation. The amount of movement is accurately measured with an electronic instrument. The instrument sends a red laser beam to a glass reflector that is aimed back at the instrument. The round-trip travel time of the beam measures distances of 1 mile or more with an error of less than 1 inch.
260.
The general shape of ground deformation above the imaginary balloon is illustrated here by a computer-generated grid. Contours of the uplift define a dome. These contours of actual field measurements at Kilauea show a similar dome, one whose center rose about 40 inches in just a few weeks. Analysis of the shape of the dome suggests that a subsurface focus, or center of inflation, is a mile or two beneath the summit of the volcano. As illustrated in this cutaway view, earthquakes occur around this center. Seismometers detect the shaking of the earthquakes, and this information is automatically relayed to the observatory by radio. Earthquakes are recorded at the observatory, entered into a computer system, and rapidly analyzed to determine location and Richter magnitude. Hundreds of earthquakes are counted during times of inflation. The zone with no seismic activity contains molten rock, a material that is too weak to generate earthquakes. The imaginary balloon thus represents a reservoir of magma stored within the volcano during its journey from the mantle to sites of eruption. More evidence of this reservoir comes from gases that escape from magma and percolate toward the surface. These gases are sampled periodically at fumaroles. In the laboratory, a sample is transferred to an analyzer to determine the types and proportions of the gases. Repeated sampling and analysis show that gases vary with time during inflation of the magma reservoir. When the reservoir inflates to its limit, magma may break out, rise to the surface, and erupt as 100-foot fountains in Halabaumal crater at the summit of Kilauea. This activity at the summit provides only part of the eruption story. Most eruptions occur on the flanks of the volcano. Magma from the reservoir intrudes laterally along a zone of cracking or rifting that extends outward from beneath the summit caldera. Such an intrusion is called a dike. The summit area subsides or deflates in response to the transfer of magma into the dike. Intrusion into the rift zone is simulated here as red water is injected into a clear gelatin model. A blade-shaped dike grows along the axis of the model. The top view, seen in the mirror above, shows how the dike follows the shape of the model, guided by stresses that result from the pull of gravity on the gelatin. Intrusion is accompanied by earthquakes that track the downrift movement of magma. The red water breaches the surface of the gelatin model. An actual rift eruption begins in a similar manner. As illustrated by this drawing, when a rift eruption stops, the dike that carried magma to the eruption cools and eventually solidifies to form a vertical blade-like body. As each dike grows in the rift zone, the adjacent south part of Kilauea volcano is pushed a few inches toward the sea, as portrayed by the arrows. Intrusion of more dikes results in more seaward push, and the process repeats until the mobile part of the volcano is highly stressed. Earthquakes occur as stress is released. Earthquake shaking triggers huge landslides. These cliffs, draped by many young lava flows, are graphic visual evidence that hundreds of feet of downward slip on landslides have accumulated during the life of the volcano. 3 landslides have taken place since 1823. Each occurred in response to shaking associated with a large earthquake, and each included several feet of downward slip. Future landslides seem inevitable. Most intrusions occur in Kilauea's summit area and along the east and southwest rift zones. Some dikes extend more than 20 miles from the summit, and in so doing they push nearly the entire south part of the volcano seaward. An important consequence of this process of intrusion and push is that the volcano grows when magma is intruded into it, as well as when lava is added to its surface. Scientists have applied many new techniques since Professor Jagger's time, including measurements of electrical conductivity of the ground and of molten magma. Magma can also be sensed with detailed measurements of the Earth's gravity field. Information obtained from these and many other techniques converge toward increasingly accurate forecasts of eruptions. Today, scientists can reach the site of an eruption almost immediately, even in remote areas, ready to carry out critical observations and measurements.
Slow down, there's a continual lava flow coming out.
Dorian, this is Elbow.
Over, do you copy? Down?
You guys will probably give you a ride into.
Yeah, this is the one Bill used.
Scientists' understanding of what happens inside Hawaiian volcanoes has improved greatly during this century. Full understanding remains clouded by the complexities of nature, but the results of future studies will surely improve the clarity with which scientists view the interior of the Earth and will help people accommodate their activities to these powerful, sometimes destructive, often beneficial, always fascinating neighbors.